the plot is going to be linear. So it will look like that straight line graph. Okay? As long as the amount of gas and pressure is constant. Okay? So we don't add or take away gas, and we're not going to change the pressure. It was also noticed that when these linear plots were extrapolated, okay, meaning when we extrapolate something from a graph, that means, say, you take a graph, okay, if I'm extrapolating, what it means is, like, say we take data. Say that on day 1, I like picking Addison. I'm just going to go with the breakfast theme. Okay? Addison has 1 orange. On day 2, she has 2 oranges. On day 3, she has 3 oranges. On day 4, she has 4. I don't know. She's just trying a new thing. Okay, guys? So if I was to extrapolate, meaning like apply what you know, the trends, and continue it in the graph, what would I say would happen next? It would keep going. That's extrapolating. So it's taking data that you have and then kind of going with the trend. Okay? See that? That's what extrapolate means. Okay, so now when these linear plots with temperature and volume were extrapolated down to 0 volume, so basically when you could get gases to become liquids, right? Because then there's no gas volume left, right? So it's when you cool them down so much that those gases will turn into liquids. So you're basically forcing a state change, okay? So all of the lines converged at one point, one very specific point. Didn't matter which gas, but they all converged at one point. What is that point called, Jessica?
Absolute zero.
That's right. You had alluded to that the other day. So, when we have our volume in liters and our temperature in degrees Celsius, you guys wrote down what you thought you would have on that graph, but most of you probably just went like this, thinking that you knew it was a linear graph because it was proportional, but, so you can erase that line if you don't have this. It actually goes kind of at a slant, so it doesn't intercept at y. It goes 0, okay? It doesn't intercept at like, it doesn't go through 0, okay? So now, this is the trend that we see with gases. Because you have to get them to a certain temperature to have 0 volume. But that certain temperature is absolute 0. So what we're going to do is we're going to extrapolate, so continue this line out. Okay, so this is different gases. So you could draw multiple lines to represent your different gases. All will converge. So these lines, these are our extrapolations. Okay, this is called extrapolated. Okay, these are lines of different gases. So they all converge at this one place. Now here, this is 0 degrees Celsius, right here. It goes past it. Okay, it's going past it. So there's a place that's colder than 0 degrees that all gases will be 0 volume. Okay? This is a very special number. Are you ready for it? Point.
0.6 or something?
No, but that's okay. You knew the first part. 273.15 Kelvin. Okay? So this, well, 15 degrees Celsius. So this point here that we call absolute 0 is negative 273 0.15 degrees Celsius. So we call that's like the 0 on the Kelvin scale. Okay? So it's like chemists, well, I'll just continue with the lesson, but it's like chemists say take this as a reference point and make a new temperature scale. Like how we have degrees Celsius or Fahrenheit, there's another temperature scale that's just more common, say, in chemistry, and it's called Kelvin. Okay, so I'll tell you about this old dead guy named Lord Kelvin. Huh? Not Kelvin spelt like Calvin and Hobbes, different spelling. Okay, so the temperature when the volume of a gas is, come on, press the button, is negative 273.15 degrees Celsius. So the volume of gas is 0 at negative 273.15. Lord Kelvin in 1848 suggested that this is the lowest possible temperature, or he called it absolute 0. He established a new temperature scale, which is called, what do you think? Right on. Yellow question. Good job. The Kelvin scale. If you had the choice to, if you had the choice